Hello guys, welcome to our today's lesson. This is Kamiti and this is Kamiti YouTube channel. Now today we are going to look at simple stresses and strains, and we got a question here that's saying as follows: the following observations were made during a tensile test on a mild steel specimen 40 millimeters in diameter and 200 millimeters long. So the observations that were made after this test on this mild steel specimen was follows: elongation of the specimen with 4 kilonewtons load 0.0304 millimeters, yield load 161 kilonewtons, maximum load 242 kilonewtons, the length of specimen at fracture 249 millimeters. Determine Young's modulus of elasticity, yield point stress, ultimate stress, percentage elongation. Now, starting with the Young's modulus of elasticity. Now, we know that the Young's modulus of elasticity is given by this ratio, the ratio of stress to strain. Now, the first thing we are going to determine is the stress, and we know that stress is given by load divided by cross-sectional area. We have a load of 40 kilonewtons. What we need to determine is the cross-sectional area of this mild steel specimen. The cross-section is circular, that's why we are given the diameter of the member. Now, the diameter of this member is 40 millimeters. When we convert it to meters, dividing this by 1,000, since we know that 1 meter is equivalent to 1,000 millimeters. This is going to give us 0.04 meters. Now, the cross-sectional area of this mild steel specimen will be given by pi over 4d squared. And this is pi over 4 multiplied by the diameter 0.04 squared, and this is going to give us an area of 1.2566 times 10 raised to the power of -3 square meters. Now with the area, we can now be able to determine the value of the stress. Now the stress will be given by a load of 40 kilonewtons divided by an area of 1.2566 times 10 raised to the power of -3 square meters. And this is going to give us a stress of 3.183 times 10 raised to the power of 4 kilonewtons per square meter. So that is the stress subjected to this specimen. From there, we need to get the strain, and therefore we know that strain is given by change in length divided by the original length. The change in length of this specimen is 0.0304. The original length of the specimen is 200 millimeters long. So we divide that by 200. And this is going to give us a strain of 1.52 times 10 raised to the power of -4. Remember, strain doesn't have units because it is the ratio of length, the same unit. Therefore, the Young's modulus of elasticity will be given by the stress over strain, and in this case, the stress is 3.183 times 10 raised to the power of 4 divided by strain 1.52 times 10 raised to the power of -4. And that is going to give us a Young's modulus of elasticity of 2.09 times 10 raised to the power of 8 kilonewtons per square meter. Therefore, that is the Young's modulus of elasticity. And so we are done with part 1 of that question, Young's modulus of elasticity. Part 2, the yield point stress. Now, the yield point stress will be given by the cross-sectional area of the specimen. Now we are given the yield load as 161 kilonewtons. Therefore, we are going to have 161 kilonewtons divided by the cross-sectional area of the specimen. We had it as 1.2566 times 10 raised to the power of -3. And that is going to give us a stress of 1.28 times 10 raised to the power of 5 kilonewtons per square meter. So that is the yield point stress. So we are done with part 2 of that question. Part 3 of the question. Part 3 of the question is asking about the ultimate stress. Now the ultimate stress will be given by the maximum load. Since ultimate is the same as maximum, will be given by the maximum load divided by the cross-sectional area of the specimen. The maximum load, we have given it as 242 kilonewtons. Therefore, 242 divided by the cross-sectional area of the specimen, 1.2566 times 10 raised to the power of -3. And that is going to give us an ultimate stress of 1.926 times 10 raised to the power of 5 kilonewtons per square meter. So that is the ultimate stress for this specimen. Finally, the percentage elongation. Now, the percentage elongation will be given by the length of specimen at fracture. So length of specimen at fracture minus the original length of this specimen, divide this by the original length. Divide by the original length of this specimen. Then we are going to multiply by 100 to get it in percentage. Therefore, the percentage elongation will be the length of specimen at fracture, 249, minus the original length, 200, divided by the original length, 200. Then multiply that by 100. And that is going to give us a percentage elongation of 24.5%. And therefore, ladies and gentlemen, that is how we go about it. Simple stress and strains. So thank you for watching our video. Please do subscribe. Thank you.